Hello everyone, my name is Payal Bhattacharjee and today I will be presenting our work on conformal sparsification for bandwidth efficient edge cloud speculative decoding. This is a joint work with Fengwei Tian, Meiyu Zhong, Guangyi Zhang, Dr. Osvaldo Simon, Dr. Ravi Tandon, and this work got accepted in NeurIPS AI4NextG 2025 workshop. Our work addresses fundamental bottleneck present in the speculative decoding pipeline in edge cloud environments. That is, the communication overhead created when the edge must transmit the full probability distribution to the cloud. Our contribution is the adaptation of principled method, conformal sparsification that significantly reduces the bandwidth while maintaining the model quality and theoretical guarantees. In this slide, I will talk about speculative decoding. In the speculative decoding pipeline, the draft model generates several tokens autoregressively, while the larger target model, the LLM, verifies them in parallel. The example shown illustrates that the correct tokens are accepted immediately, the green check marks, while the incorrect ones are rejected and resampled by the LLM. This technique significantly increases the decoding speed compared to the traditional autoregressive decoding because of the parallel verification. However, for edge cloud deployment, we face a challenge. The draft model must still send the probability vectors to the cloud, and these vectors are usually huge. Speculative decoding is already used by major LLM providers such as OpenAI, Google's Gemini, Anthropic's Claude, Amazon AWS, and so on. But in an edge cloud setting, as I mentioned earlier, transmitting dense probability vectors become the main communication bottleneck. Each token requires sending a v-dimensional probability distribution, often hundreds of thousands of values, and we have seen typically they are 30K to 50K long. So, our goal is to reduce the communication without degrading the acceptance accuracy. In this slide, I will talk about the need for sparsification and quantization in edge cloud speculative decoding. Since the token distribution is extremely sparse, most of the mass lies in the top K tokens. This motivates sparsification. We keep only the important or the high probability tokens and drop the low probability tail. But we still need to efficiently encode the retained values, which motivates quantization. Together, this enables fast, low bandwidth communication from edge to cloud during speculative decoding. There are two main sparsification strategies that we investigate in this paper. The first one is top K sparsification, that is non adaptive and that always keeps the highest K probabilities. The second one is conformal sparsification, which is adaptive thresholding, retaining all the tokens above a learned threshold beta t at iteration t. Our method builds on the conformal version because its adaptivity aligns better with uncertainty variations across the decoding steps. This adaptivity is crucial in speculative decoding, where the distribution shape can vary significantly from step to step. So, this is the full proposed framework of our paper. The Edge SLM or the small language model first computes the probability distribution Qn of t at the iteration t. Then we apply conformal sparsification to keep all the probabilities above beta t and drop the rest. Then the threshold beta t is updated using a calibration rule designed to control the drop probability mass as highlighted in the slide. Next, we quantize the sparse vector using lattice-based quantization to obtain a compact representation. This compressed representation is then transmitted to the cloud where the LLM verifies the draft tokens and resamples when it's necessary. In the paper, we also provide some theoretical analysis and guarantees. The first theorem provided in the paper shows an upper bound on the expected number of rejected tokens. The bound decomposes into two sources, the SLM LLM discrepancy and the distortion introduced by quantization and sparsification. The key insight is if we control the drop probability mass, then we can actually control the rejection rate. The second theorem shows that under a simple learning rate rule, the average drop probability mass converges to the target alpha. Thus, conformal update guarantees asymptotic calibration, a crucial property for reliable decoding. This slide shows some empirical analysis results on LM1B dataset. The figure on the top compares KSQS and CSQS in terms of latency and resampling rate across temperatures. Temperature has a major effect in the performance of both KSQS and CSQS. Higher temperature widens the distribution, making sparsification sometimes less effective. However, both KSQS and CSQS significantly reduce latency and resampling rate, with KSQS proving more effective in low uncertainty regimes, i.e., the low temperatures, while CSQS achieves most favorable balance under high uncertainty regimes, that means in the higher temperatures. These results highlight the potential of distribution aware compression to make edge cloud LLM inference more practical and scalable. To summarize, our conformal sparsification and quantization framework compresses token distributions efficiently. SQSSD reduces bandwidth and latency without sacrificing the acceptance accuracy. The KSQS method works well in low uncertainty settings, while CSQS is more robust in high uncertainty environments, making it ideal for real world edge cloud LLMs. This is a step towards scalable and communication efficient LLM deployment on edge cloud environment. Coming to the references, so these works collectively provide foundations for our sparsification strategy, quantization framework, and the latency distortion trade offs underlying our theoretical guarantees. Our contribution unifies these ideas into a single, conformal adaptive pipeline suitable for real world bandwidth limited speculative decoding. Thank you.